Now, another application of the derivative, more specifically the chain rule and implicit differentiation, would be related rates. Because we are going to find rates of change of two or more variables with respect to time. So here are some guidelines, although we don't follow all step 1 and step 6 in all problems, but here are some guidelines that you can use in solving word problems involving related rates. So if you can draw a figure to help you visualize the situation, that's good. Then name the variables that will be used to solve the problem. Remember that t is for time, and we have to assume that all variables are differentiable functions of time. T, x, t. We write the given, and of course, the on is asked. Then relate the variables by setting up the equations to be used. Differentiate implicitly in terms of t that evaluated answer b. So let's have some examples for related rates. So first, we have a ladder that is 25 feet long leaning against a vertical wall. The bottom of the ladder is pulled horizontally away from the wall at 3 feet per second. How fast is the top of the ladder sliding down when the bottom is 15 feet from the wall? So let's draw that to visualize. So we have a vertical wall here. Then we have a ladder. That's our ladder. The ladder is 25 feet long. And it's being pulled away from our wall. Pulled away from our wall at 3 feet per second. How fast now is the top of the ladder sliding down? How fast is that going? When the bottom is 15 feet, so this is already 15 feet from the wall. So there. Now since we're asking how fast, and we already mentioned that when it comes to rate of change, derivative would all be speed or velocity rather, speed or velocity. So what we're looking for is the velocity as the ladder slides down. Now at first it may seem, what relationship can we use? There's no mention of any shape, any figure, any formula that we can use for problem number 1. But if you're going to take a look at the shape, that's formed, we actually have, we actually have a right triangle. And since what we're given are sides of the right triangle, then we can say that the equation that we can use here would be the Pythagorean theorem. Since this would the Pythagorean theorem, and since we're in calculus, I'll make this x as horizontal, y for vertical. Becomes x squared plus y squared would be equal to our hypotenuse, and since the height of the ladder doesn't change, doesn't chop in between, it will always be 25 squared. So there. So if we want to figure out how fast this is going in terms of time, we would need to differentiate this equation in terms of time. So therefore, differentiating this in terms of time, going to have differentiating x squared, that's 2x dx over dt plus 2y dy over dt is equal to 0. Now, take note that we have to place dx over dt because we have to place dx over dt and dy over dt because this is the one that tells us that these are differentiable in terms of time. So you would always find the d over dt in your other variable, and that is very important because these would actually be rates. In this specific case, dy over dt is what we're looking for. This, the one that's going down, is actually dy over dt, the rate that this vertical side goes down or gets shorter. This 3 feet per second is your dx over dt because that affects the length of the horizontal side. And the length of the horizontal side at that specific moment is 15. So we have values of x, we have dx over dt, and we're solving for this. So plugging in the values that we have 2 times, we mentioned x is 15, times dx over dt, that's 3 feet per second, plus 2, now here. We did not mention any value of y. But what we're solving is dy over dt, so it should be only dy over dt that we do not know. Hence, we should have a value of y. But as you're going to see here, we have 25 feet that's constant and we have 15 feet. So therefore, we can solve for y. So, if we solve first for y, we're going to have 15 squared plus y squared is equal to 25 squared. Y squared will be equal to 25 squared minus 15 squared. And that would be actually equal to y squared is equal to 400. Y would get in the square root of that. Y would then equal to plus minus 20. But since that's length or distance, so y is equal to positive 20. That's what we input there. It's 20. Then dy over dt is equal to 0. So solving for this, what we have, that's 6 times 15, that's 90, plus 40, 40 dy over dt is equal to 0. We transpose that. 40 dy over dt is equal to negative 90. Dividing both sides by 40, we're going to have dy over dt is equal to negative 9/4. Now, that is actually quite consistent because as you can see here, it's going down. So since it's going down, it has to be negative. So the velocity is negative 9/4 feet per second. That's how fast the ladder is sliding down. Now let's go to number 2. In number 2, a spherical snowball is being made so that its volume is increasing at the rate of 8 cubic feet per minute. Find the rate in which the radius is increasing when the snowball is 4 feet in diameter. So we have a snowball. This will be for the other. So since it's a ball, let's here that's is. So the volume is increasing at a rate of 8 cubic feet per minute. So it's a rate, so that's the dV over dt, 8 cubic feet per minute. That's a rate. Find the rate in which the radius is increasing. So we have to solve for dr over dt. When the snowball is 4 feet in diameter, so if its diameter, it's like that, and this entire diameter is 4 feet. Since it's spherical, you will have an idea of the volume of a sphere. The volume of a sphere is given by 4/3 pi r cubed. If we are now to differentiate this because we have to involve the rates, dV over dt will then dV over dt will then equal to 4/3 pi times 3r squared dr over dt. Cancelling 3, dV over dt will then be equal to 4 pi r squared dr over dt, which tells us that we would also need later on r. But the 4 feet is diameter. We all know that if diameter is 4 feet, we just need to divide it by 2 to get the radius, which in this case is 2 feet. So now we have everything that we would need. Our dV over dt is 8 feet per minute, that is equal to 4 pi times our r of 2 squared, then dr over dt. And this is what we would have to solve. So, simplifying this, 8 will be equal to 2 squared is 4 times 4, that's 16 pi dr over dt. Dividing now both sides by 16 pi, 65, 65, this is cancelled. Therefore, dr over dt, or the rate by which the radius is changing, is 1 over 2 pi feet per minute. So, by the time, by the time that the diameter of the snowball is 4 feet, the radius has been changing 1 over 2 pi feet per minute. Let's now go to number 3. Sand is being dropped at a rate of 10 cubic meters per minute onto a right circular conical pipe. If the height of the pad is always twice the base radius, of what rate is the height increasing if the pad is 8 meters in height? So we better draw that here. So let's write and draw what's given. So we have sand being dropped at a rate of 10 cubic meters per minute on the right circular conical pipe. So we would have a right circular conical pipe, and sand is being dropped by 10 cubic meters per minute. 10 cubic meters per minute. And since it's cubic meters, this would be your dV over dt. It's cubic meters, so it's volume. Now, the height of the pile of the sand, for example, your sand is like this. So the height, for example, this is where your sand is already. The height of the pile of the sand, height, is always twice the radius. What is now the rate of the height? What rate is the height increasing? So it's dh over dt when the pile is 8 meters high. Each is 8 meters. So let's look for the volume of our cone. The volume of our cone would be 1/3 pi r squared h. We have to be very careful here because at this point we have 3 variables, v, r, and h. Most of the time we only have to work with 2. So because if we have to find the derivative of this, it will be a multiplication at this not multiplication. Product rule, we're going to use product rule. Now use the product rule between r squared and h. So it would be better if we can already express this as just v is equal to a function of just 1. In this case, h, because that's what we're looking for, dh over dt. We have this idea that h is equal to 2r. Height is always equal to twice the radius. So we can substitute r here if we have to solve for r here. So solving for r here, we divide both sides by 2. R will be equal to h over 2. And that's what we substitute here. So v will be equal to 1/3 pi times h over 2 squared times h. So now you have an equation in 2 variables, one independent, one dependent. So v will then be equal to 1/3 pi times h cubed over 8. So that it will be easier for us to find not 8, 4. It's h cubed, correct, but it's 4. So overall, if we are to simplify this volume, this becomes volume is equal to pi h cubed over 4. So now we can find the derivative to find h over dt. So therefore, dv over dt will then be equal to that's pi over 12 times 3h squared ph over t. And t over 12 becomes 1/4. So therefore, I'm going to have dv over dt is equal to pi over 4 h squared ph over. So substituting our values at this point, this becomes 10 is equal to pi over 4. The height is 8, so times 8 squared times ph over. So Therefore, I'm going to have 10 is equal to pi over 4 times 64 times dh over dt. This gets cancelled. I'm going to have 10 is equal to 16 pi dh over dt. Dividing both sides by 16 pi to solve for dh over dt. 16. Therefore, dh over dt will then be equal to 5 over 8 pi meters per minute. At the height of 8 meters, it's the height has been changing at 5 over 8 pi meters per minute. Let's now go to number 4. A television camera at ground level is filming the lift up of a space shuttle that is rising vertically according to the position function s is equal to 50t squared, where s is measured in feet and t is measured in seconds. The camera is 2,000 feet from the launch pad. Find the rate of change in the angle of elevation of the camera in 10 seconds after liftoff. So let's try to draw our problem. Use this is 4. So a television camera at ground level. So this is the ground level. And this is the camera. Then the space shuttle lift off. Okay. And it's rising vertically according to the position s is equal to 50 squared. The camera is 2,000 feet from the launch pad. 2,000 feet from the launch pad. We're asked to find the rate of change of the angle of elevation, that's d theta over dt, at the camera at t is equal to 10 seconds after liftoff. So, although it looks like a right triangle, it would be important because what we're looking for is the rate of change in the angle of elevation. So, since it's angle and it's a right triangle, we need to deal with trigonometry. Now, with that, we can see that this is the angles. The given is this and this. That's opposite and adjacent, which gives us the tangent function. So, the tangent of angle theta would be the opposite side. Going to use 50t squared already. 50t squared over 2,000. So we only have one variable, t squared t, and then simplifying that, tangent theta, the final function will be tangent theta is equal to t squared over 4t. So since we now have to find derivative of that for dt over dt. Differentiating the function, I'm going to have secant squared theta d theta over dt will then be equal to 1 over 40, actually that's 2t only, because it's already a function of trigonometry, theta over dt is 1. This gets cancelled, therefore secant squared theta d theta over dt is equal to, this becomes actually 20. This becomes t over 20. Now, solving for d theta over dt, just like it first, we divide both sides by secant squared theta. Dividing by secant squared theta is the same as this is now the same as d theta over dt is equal to t over 20 times 1 over secant squared theta, which would actually be the same as d theta over dt is equal to t over 20 times cosine squared theta. Now the question is, we have t, then what is cosine squared theta now? That's now the question. So if we're going to take a look at what we're given, based from this relationship, what we can infer is that maybe we can solve for cosine theta at t equals n seconds. So, tangent, I'll write it here then. Tangent theta will then be equal to 10 squared over 4t. So, tangent theta will be equal to 100 over 4t. This then gives you y, and this then gives you x. So, if we can then solve for h, we can then find cosine, because if you remember, cosine will be x over h. What am I talking about? This is y. This is the value of y. This is the value of x. So, but just round it off in terms of the values, because we already rounded off here. So, we need to solve for h. And since it's a right triangle where you can have x squared plus y squared is equal to h squared. So, in this specific case, I'm going to have h is equal to the square root of x squared. That's 100 squared. To show h squared is equal to it's 100 squared plus 40 squared is equal to h squared. So I'm going to have, that's 10,000 plus 1,600 is equal to h squared. So we're going to have 11,600 is equal to h squared. Divide both, not divide, square both sides. H will then have a value of 20 square root of 29. So with that in mind, solving it here, oops, I forgot theta. Cosine theta will then be equal to x value of 40 over the h value of 20 over square root of 29. So cosine theta becomes 2 over square root of 29. Although we would not need to rationalize this anymore, because what I need here is cosine squared. So squaring both sides, cosine squared theta is equal to 4 over 29. So therefore, I now have the value for cosine squared theta. So going back, d theta over t is equal to t, which is 10. That's 10 over 20 times 4 over 29. There you go. This actually gets cancelled with this constant. So this gets 2. Therefore, the rate of change in the angle of elevation is 2 over 29. Our units would be, this is in radians, so radians per, let's check the unit of time, seconds. Radians per 2 over 29 radians per second. There you go. And those are sample problems related to another application of derivative, which is the related rates.